And so that's it. So good evening to everyone. I'd just like to welcome you here this evening. My name is Daniel Manning, and I'm the Secretary of the Cork branch of the Institute of Marine Engineers, Science and Technology. And on behalf of myself and Liam Doyle, the Chairman of the Institute, I'd just like to say thanks very much for joining us this evening. I'd also like to just say hello to our colleagues there from IEI, and in particular the Cork branch of the Institute of Engineers Ireland, who are after joining in with us tonight as well. Also, I'd like to welcome Mark, who's our speaker tonight. And actually, Mark is in Jakarta at the moment in Indonesia, and it's 1 o'clock at night. So again, thanks very much for doing this. You should be in bed asleep.
No problem.
So as we saw just on the advertisement, Mark is a native of County Waterford, and he's been involved with the design and deployment of hydrogen-based fuel cells for microgeneration and stationary power applications. And it's mainly in remote villages in Asia and Africa. Mark is also a consultant with Rix Industries. They're a US-based company. And hopefully tonight he'll be able to provide us with an insight into the use of methanol-based hydrogen power systems that are being designed for the marine environment and shore power. So just some housekeeping. If people can just keep their microphones on mute, and we'll do a questions and answer session just at the end. So if anyone has any questions, just pop them in the chat box, and we'll pick them up as we're going along. So I'd just like to say welcome, and the stage is yours, Mark.
Okay, great. Thank you all for your time and attention. It is 1 o'clock in the morning, but I'm used to it, unfortunately. I have to share multiple time zones in my normal daily career. So I just got to see if I can share my screen now. So let me try this. It worked a few minutes ago. Okay.
Yeah, so we can see that, Mark. Yeah.
Yeah, all right. So, okay, that kind of works on my end too. Perfect. Okay, so thanks, Dan. Yeah, as Dan explained, I've been involved in the hydrogen fuel cell space for about probably the last 10 years now. And most of the sort of work I've done really has been using fuel cells and hydrogen more as an energy storage medium. So as an alternative to batteries, basically, as an alternative to using diesel generators to extend the range of batteries or to provide a backup. And yes, most of these applications have been in remote places because that's really where this type of technology works quite well. I guess I should mention my sponsor here, Rix Industries. So Rix Industries is a US-based company. They've contracted me about a year ago to help them really define and design where they're going in terms of this wonderful business. Rix as a company are predominantly involved in providing high pressure pneumatics and gas transfer solutions, including large compressors, gas generators, and liquefiers for a wide range of military and commercial applications. Most of their customer types are military, marine, navy, air, and pretty much quite demanding environments. So their sort of decision to get into hydrogen is sort of based on the fact that they see this as being a big sort of way forward, particularly in the marine industry. Rix as a company is quite unusual. They're actually formed in 1878, so they're about 143 years old, which is quite unusual. So their clients as such include the U.S. Air Force, Boeing, Lockheed Martin, NASA, Northrop Grumman, and those type of clients. The sort of solutions that they demand are obviously they have to be very high performance, they have to be very durable, and they have to last for the service lifetime of the vessel, which is very similar to what I have to do with microgrids. If I'm deploying something in a remote location in the middle of, Asia or Africa, basically that has to last unattended and survive for a minimum of 10 to 15 years with minimal maintenance. And in the marine industry, the marine space, where pretty much looking at the same type of requirements. So I guess why are we here? Well, okay. So why are we here? Right. Well, I guess the maritime industry, I mean, you've all been challenged by the IMO to reduce carbon intensity. And what does that actually mean? Well, it means carbon dioxide produced. I think the way they phrase it is carbon dioxide produced per ton mile on a vessel. So referencing back to 2008, I think the IMO requirements were that carbon intensity reduction had to be reduced by 40% by 2030 and by 70% by 2050, which is quite a challenge indeed. So I guess the big question is, what do we need to, how do we get to this place? What do we need to do? And I think the simple answer is we need to find more effective ways as an industry of reducing our carbon footprint. And I guess that can be achieved in some ways by building bigger boats, by reducing specific fuel consumption on existing vessels, maybe by designing better hulls, new ship design or whatever. But whatever we do, it's only going to really get us part of the way towards achieving these milestones. And really what we need to do is find a way to reduce our carbon footprint further. And obviously I'm a firm believer that hydrogen fuel cells offers that solution. Now, the fuel cell is half the problem. The second part of the problem is, where do I get my fuel? And I think methanol as a fuel for marine is an ideal carrier of hydrogen. And more importantly, if I can produce hydrogen on board the vessel, and I can produce enough to displace generators or engines on smaller vessels, etc., these IMO targets, potentially could be achieved. So I guess the first thing is to explain, what exactly is a fuel cell and how does it work? So the fuel cell is a source of clean, stable power, which produces no emissions. That's pretty much how they work. Their exhaust is water, and they're quite happy to produce electricity and heat as long as fuel to that fuel cell is, in this case, hydrogen, is supplied. So in one sense, fuel cells act a bit like a generator in that they need fuel. However, they also act like a battery in that the electrical power produced is based on a chemical reaction, not a mechanical reaction like a diesel generator. So I guess you could consider, or you could sort of think of fuel cells as generators that do not have any moving parts. And if you don't have any moving parts, it means less maintenance. It means no consumables like oil or oil filters, belts or lubricants. So a fuel cell itself, consists basically of two electrodes, a negative electrode or anode and a positive electrode or cathode. And these electrodes are sort of sandwiched around an electrolyte, which is sort of shown by the sort of purple symbol here. The fuel, in this case, such as hydrogen, is fed to the anode, and air is fed to the cathode. And the barrier or in between basically sort of separates the two gases. And the most common form of fuel cell, or the name that you hear most mentioned, is generally referred to as a PEM fuel cell, a proton exchange membrane, where that catalyst, or that barrier that separates the two gases, is based on a platinum catalyst. And its job really is to separate or to split the hydrogen atoms into positive hydrogen ions or protons and negatively charged electrons, which take different paths to the cathode. So the electrons go through an electrical circuit, and that process is what creates a flow of electricity. The protons migrate through the electrolyte to the cathode, where they unite with oxygen from the outside air and the electron to produce water and heat. So a single plate like this picture on the left would typically only produce 1 volt in terms of power. So barely enough energy for even the smallest appliance. So to increase the amount of energy, we put a bunch of these cells together like a sandwich to form what we call a stack. And the sort of stack sizes that we can generally build now can range from a couple of 100 watts up to around about 100 to 150 kilowatts, which would be the norm large size for large scale power applications. And we can parallel these together as well. So we can make 100 watts to produce 400 kilowatts, for example. Now, as I mentioned, there are many types of fuel cells out there, but PEM is the most common for applications such as ours, as these fuel cells operate at relatively low temperature. So when they're operating, they may be operating at between 80 to 100 degrees. And also their ability to, if you like, to react or to vary their power to meet the load requirements is actually quite efficient and fast. Yeah. So let me just, so I just want to briefly touch on, one or two sort of differences between diesel generators and fuel cells. So one area that's often talked about is this topic of efficiency. Yeah. So I guess historically, diesel generators are always operated at what you would call part load. And it's simply because when you size a diesel generator, or when you figure out, which one you need, the DG size or the generator size is normally specified in accordance with what you think is the maximum power required. And that's normally calculated based on what your attached circuits or what your individual loads are likely to be. So this sets the 100% load point, which is generally very rarely ever encountered in practice. Or even if it is, it's never really running at full load for any sort of appreciable amount of time. Yeah? So the issue that you have with diesel generators is at part load, its operation is really suboptimal, and this results in many issues, for the diesel generator itself. So in addition to maybe having an increased fuel consumption because I'm operating at lower efficiency, that can result in increased pollutant emissions. Operating at diesel generators at any kind of a part load generally has these sort of issues mentioned at the bottom, like I have development of hydrocarbons, by sticking rings, I can start damaging the pistons, glazing the cylinder walls, I can create a wet stacking type environment, and I can also end up burning more oil. Yeah? So basically DGs are normally sized for peak demand, but the basic problem in most situations is they're normally run at part load, which is usually the brunt of most of the problems. Now, if you look at the graph on the right, it sort of illustrates the sort of differences here in efficiency. So between a diesel generator and a fuel cell. So fuel cell efficiency is different. It's a chemical reaction, and as such, its efficiency can increase as the load is increased from. So if I go from 100% down to 50%, my efficiency will effectively still be the same. Huh? So diesel generators, by contrast, the diesel efficiency, it usually decreases from 100% down through all parts of the load. Huh? And DGs, if you size them for peak demand, but you run them at part load, you end up having low efficiency, you end up having more emissions, you burn more fuel, you're really to provide the same amount of power. Huh? So there's quite a number of reports. I mean, fuel cells have been tested in the marine sector for a number of years now, and there's some quite interesting reports out there. But one of the first ones that I remember seeing, which really brought a lot of this home to me, was a hydrogen fuel cell generator, which was developed for a port in Hawaii. Yeah? It was actually installed in Honolulu. And the basic idea here was to look at some situations in the marine port environment that could take benefit of using fuel cells instead of DGs, where they would be able to compare historically, how both types of solutions were designed. So the project they looked at was doing shore power for reefer containers. So in Honolulu, they get a lot of containers that cargo ships come in with, maybe 50, 60 refrigerated containers. And these are normally dropped on the side of the port. And historically, a diesel generator in a 40-foot container or 20-foot container would be dropped down beside these reefers. And its job would be to power the reefers for the duration they were there. Yeah? So what they did by comparison was they put together a 100 kilowatt hydrogen fuel cell with 72 kilograms of hydrogen stored in high pressure vessels. And the issue really that they wanted to test was how this would be accepted in terms of normal marine safety and regulations, because in the US, there's a ton of regulations. So I think they had people from, they had a hydrogen safety panel, which consisted of people from the US Coast Guard, the American Bureau of Shipping. Young Brothers was the company itself, who were the reefer management company. And they ran this system for 10 months, 10 months to a year. And the end result was that a report was generated, which I can share with you guys, no problem. And the report basically confirmed that historically, the DGs used to power these reefers were on average really only operating at 30% or part load. And the result of using fuel cells, they were able to get reduce emissions by 35%. Yeah, and it also sort of provided avenues and approaches to how this could be widened for further adoption with other sort of uses in the same marine port. Yeah? So the graph on the left shows the result of some of the tests where the fuel cell was used to power reefers. And what this illustrates is the amount of fuel burned per kilowatt hour, in this case hydrogen, compared to, say, the equivalent amount using a diesel generator. And it can be seen that the fuel burn of a diesel generator increases as the load is reduced, which is not what you would expect. While with a fuel cell, if the load is increased or reduced, the fuel consumption remains relatively constant against the load itself. Yeah? So part load behavior of DGs also has an adverse effect on air emissions. I mean, the figure on the right here shows that the air emissions for the same diesel generators operated at part load. And in all cases, the air emission per kilowatt hour of energy produced becomes worse as the load is reduced, which is kind of counterintuitive. Yeah? This report, by the way, is provided by Sandia, and I think it was published in 2017, but it's pretty relevant for today. Yeah? So the next big question is, okay, let's accept that fuel cells are more efficient at hydrogen than diesel generators. But the big question here is, where do I get my hydrogen? That's the big problem. Where do I get my hydrogen? And if I'm in a ship or I'm in a busy port environment, where do I put it? And how do I get at it? How do I refill? So just a couple of quick mentions in terms of hydrogen itself. So hydrogen has a couple of physical attributes that obviously are very unique to hydrogen itself. I guess the first unique attribute is if it is released or escapes, it actually evaporates extremely fast. Basically, if I have a leak in a tank or a sudden rupture of a tank, I can actually I can assimilate 4,000 gallons of hydrogen gas in about 7 seconds. That means in 7 seconds, 4,000 gallons of hydrogen actually assimilates itself into the environment around you. Hydrogen is extremely buoyant. So if it is released, it goes straight up. And it goes straight up at an average speed of about 40 miles per hour. Yeah? So it goes straight up very fast. Now, hydrogen, obviously, it can ignite if it has access to an external flame source. And it could also ignite to a flame in the right mixture, but to get to that is actually very difficult to do. Yeah? So I'm not sure if you've seen these advertisements for gimmicks for cars where people are offering you the ability to put an electrolyzer into your car and to cheap electrolyzer into your car and to produce hydrogen, and which you then put into the carburetor. What those things are actually doing is they're making hydrogen and they're making oxygen, but they're putting HHO, which is hydrogen and oxygen mixed together into your carburetor, which is extremely explosive. But hydrogen in itself is generally okay as long as it doesn't get to an ignition source, which is a similar type issue, I guess, from a safety perspective, as if you were dealing with LPG or another gas. Yeah. But in terms of the burning question, where do I get my fuel? There's really two approaches to doing this, and I call them reforming and recharge. But basically, it really means making hydrogen through a process like water electrolysis, storing it in a vessel, which has to be stored at high pressure, so you can store a meaningful amount of hydrogen, and then you suck the hydrogen from the vessel when you need it, yeah? And then you replace the vessel when it's full. That process of recharging is historically what I've done for remote villages and remote places, where I'm using solar panels and the excess energy that's not being used at the time of day to stockpile hydrogen in a pressure vessel, and then I use that later. I'm sort of time shifting, you know, in that case. The more practical way to do this, I believe, in the marine environment is to do on-site reforming of a hydrogen carrier fuel like methanol. Now, basically what this means is my hydrogen is in a liquid fuel format, and that liquid fuel, or my methanol fuel, if you like, I reform that to produce hydrogen only when I need to. So hydrogen as a gas really only exists on the pipe that connects my reformer to the fuel cell stack. So this really is in a nutshell, the two sort of ways of getting hydrogen to where it's actually needed. Yeah. So with reforming, in a lot of cases, I can do that actually on the vessel or in the location where I need my power. With recharging, I generally have to stockpile it somewhere and then, you know, bring it to the fuel cell and maybe a smaller vessel, and then use it and then replace it when I actually need it. So I guess from a marine perspective, what really drives the decision in terms of which way you go is you care about, well, first of all, marine is a big consumer of marine diesel. Yeah? I mean, 370 million metric tons of bunker fuel per year is not going to be replaced by an alternative fuel source overnight. Yeah? This kind of adoption takes time. Yeah? I think the second issue, and again, towards meeting future emission standards, is whatever route you go, there still has to be a pathway to further low to no carbon carbon reduction. So, for example, right now today, most of the methanol is produced through coal reforming. So that's not very CO2 friendly. Now, when I use methanol to produce hydrogen, the result is, yes, I'm producing lower emissions while I'm doing that, but the methanol itself, as it stands, may not be, you know, friendly. There needs to be a pathway where eventually that methanol becomes, you know, more carbon friendly. And there's already manufacturers that are producing what they call green methanol, where they're producing methanol by taking hydrogen produced from solar, by adding CO2, by adding carbon from the environment, and using that to produce, you know, green methanol. So if I'm using green methanol, then I'm getting closer to the point of really zero emission type fuel source. Yeah? Obviously, a big issue with marine is price. It's got to be price competitive. So, you know, in my part of the world, in Asia, most people, the only green they care about has got Benjamin Franklin's face on the front. They're assuming that by going to a green, renewable energy approach towards things, they're going to have something that is more reliable and over a longer period of time will end up costing less money. The reality, you know, is that that's quite hard to do. Yeah. One of the things that I'm finding quite refreshing about marine is the marine environment and the marine space, because it's so heavily regulated. You're forced to do something because it's mandated, not because you want to make more profit in your business. Yeah. And that's, you know, one reason why I'm really like marine at the moment. Also, you know, the source of this fuel has to be, you know, available globally. Pretty much any port you go to in the world, it should be no problem getting your hands on methanol. And methanol as a fuel itself is probably one of the most widely carbon-based fuels other than diesel that's produced and distributed around the world. Methanol itself is used in a whole lot of other manufacturing processes, anything to do with plastics, paints, electronics, all requires the use of methanol. And I guess methanol, say, when I compare it to diesel or petrol, it's not a very political type fuel. So the methanol prices are generally quite stable. You can go to methanex.com or in these websites and you can see that, you know, a metric ton of methanol is $310, and it hasn't really changed much like that for the last 6 or 8 months. The volatility and supply is probably a little bit easier to deal with and to manage than, say, you know, diesel and petrol, for example, which is more politically managed, shall we say. And finally, safety obviously is going to play a big factor. Now, one of the aspects about methanol that's quite interesting is the management and the logistics of dealing with methanol. In the marine environment, the existing processes and bunkering and facilities that are currently used for diesel will also work. I mean, methanol as a fuel can be handled in the same way as you're currently handling diesel. So, for example, if I want to get fuel to my power generation system and it's floating on a barge, and historically, if I used to put fuel on a boat and bring it to the barge and pump it from the boat to the barge, you can do exactly the same with methanol. So from the safety processes and procedures wise, the approach to will be similar. Not exactly the same, but they'll be fairly similar. Yeah? Okay, so just if we talk about the word efficiency, because it keeps coming up in conversations here, but I just want to briefly touch on the chemistry in terms of what's actually happening here. So methanol is one of the simplest alcohols, and it reacts readily with water. And the combination of methanol and water can generate hydrogen and carbon dioxide. Now, the energy that is applied to make this reaction occur at reasonable rates is basically thermal energy. It's not electrical energy, which would be if you were to use electrolysis to produce hydrogen. And that's quite an important distinction when compared to other renewable pathways to hydrogen. So ideally, when we heat methanol and water, we get hydrogen and carbon dioxide from this reaction. But in practice, we also get some carbon monoxide, some CO. And because of that, it's necessary for us to purify the hydrogen that's produced. And you know, if that hydrogen is going to be used in a PEM fuel cell, then our system automatically purifies it to 99.99% purity. If that hydrogen that's being produced, you want to stick it into a combustion engine and use it as a fuel in a combustion engine, then we don't care so much about the CO. Yeah? But for the purposes of a low temperature fuel cell applications, we need to pay attention to that carbon monoxide contamination, and that sort of ability to purify that hydrogen further and to remove that is already built into the hydrogen generation system produced by RICs. Yeah? So I'll explain more on how we actually do that. But just finally, when people talk about, say, using water electrolysis as an alternative pathway to produce renewable hydrogen, I mean, yes, it's a very mature technology. It's been deployed in large scale, pretty much around the world. There's nothing wrong with it at all, except for the fact that it uses a lot of electricity to produce hydrogen. And to be more specific, I need 50 to 55 kilowatt hours of electricity to generate 1 kilogram of hydrogen by electrolysis. So to say that in another way, if I have a megawatt of electricity applied to an electrolyzer for an hour, I will get 20 kilograms of hydrogen. Now, in comparison, that's actually not a lot. If I consider methanol reforming as an alternative, I actually need very little electricity. I actually need about 0.04 kilowatt hours of electricity per kilogram of hydrogen. And again, the energy to react methanol with water is thermal energy. And thermal energy is, at the end of the day, much more cheaper than electricity. Electricity is perhaps the most expensive form of energy that we have available to us. Yeah? So if we look at thermal energy that's used to reform methanol, it's only a modest amount of about 7.5 kilowatt hours to produce the same amount of hydrogen. Yeah? So what do the systems look like? Well, we've basically got two versions of the system, a small one and a big one. There is a third one in the pipeline, which is a really big one, and that will be basically twice the size of the big one here. So on the left, the small unit on the left is what we call the S series. It's typically used for small stationary type power applications. That little system will produce 0.7 kilograms of hydrogen per hour. And 0.7 kilograms is about 130 liters per minute. And that augurs well or matches up well to, say, a 10 kilowatt fuel cell. So 130 liters per minute or 0.7 kilograms per hour is enough hydrogen to power a 10 kilowatt fuel cell quite happily. On the right-hand side, we have the larger system, and its production rate is basically 10 times more. It's just shy of 10 kilograms of hydrogen per hour, and or 1,300 liters per minute. And that is really sizes itself up well for something in the region of 100, a fuel cell that is capable of producing 100 kilowatts of energy. And the bigger system, it's been built really to design so it can go on a ship or a truck or any sort of use for mobility type applications. Now, just to, I guess, explain how it works. So my fuel is not just methanol. It's methanol and water, which is actually quite interesting. In terms of the percentage by weight, it's 62.5% methanol, 37.5% water. So yes, if you can imagine I'm a ship, a third of the hydrogen I'm produced actually comes from the water I'm sitting in. That is theoretically quite possible and very interesting. So in the case of a ship, for example, I don't have to carry water. I'm already processing water. Most ships are processing water, which they get from the environment that they're in anyway. So methanol mixed with water is obviously, with the water I need to deionize and desalinate it, but yes, it can be drawn and purified from the environment I'm sailing in. So the methanol water mixture flows through a heat exchanger into a catalytic converter, and the catalytic converter basically converts heats the liquid up to a steam, and from that steam a catalytic reaction occurs, which basically splits hydrogen, creates hydrogen with carbon dioxide and some other gases. But it does this without the release of SOx or NOx or any particulates whatsoever. So this gas mixture, it flows through a purifier, and this purifier is the sort of the IP, the secret sauce behind the design of this system. The purifier separates the hydrogen from everything else and produces hydrogen at a purity rate of 99.99%. The waste fuel gas, if you want to call it that, or whatever, we feed that back into the burner, throw more fuel on top of it, and that, if you like, recycled waste gas is used to maintain the temperature of the reformer. So the secret sauce here really falls into two areas. It's maintaining the heat, which is about design from mechanical design point of view, the efficiency of being able to do that, and the way that we're able to reuse some of the waste gas towards keeping that heat process going. So once the hydrogen is produced, it goes into a buffer tank where it's stored temporarily, waiting to be used. And this buffer tank is, if you like, it's our interface to whatever application actually wants to use the hydrogen itself. Now, in the future, some of this reformant gas is produced in the form of CO2. So yes, there is some CO2 produced as a result of this process, but in future we'll have the option of capturing carbon dioxide from the system itself, and either producing zero CO2 or that's something that I think is actually very possible in the future. Now, let me just, okay. Yeah, so I mean, obviously, ultimately, we want to drive the overall carbon intensity to a low, if negative value, if possible. Yeah, and I think that's that's potentially doable. Yeah? So, just to give you a sort of, if you like, integration example. So, to integrate a hydrogen generator with what I'm going to call a hydrogen consuming device, the integration process is to be quite simple. And the hydrogen consuming device can, in case of the left side here, can be a compressor. So and this would be a classic example if this system was used to provide fuel for a hydrogen refueling station for cars or trucks, for example. The the main sort of point is that we produce hydrogen, it goes into a buffer tank, and the buffer tank is controlled by the application device itself. So in this case, the compressor is what's basically telling the taking hydrogen from the tank and causing the reformers to produce more. The system on the right example here, in this case, the load, the hydrogen consuming device is a fuel cell engine, if you want. And the fuel cell engine is basically being driven by the load demand that's applied on it. And in this example here, the fuel cell and also a battery bank are connected to the same load bus. And this generally is what would be typically seen in most power applications. So the fuel cell works well with the battery because the battery itself can react quite quickly to peaks and spikes from the load, and the fuel cell can basically backfill the battery by maintaining relatively high power output at the same time. So for dynamic loads, if you like, then this sort of combination of using a fuel cell with a small battery is quite common. And in both cases, the fuel cell is simply reading pressure from the buffer tank, and the hydrogen generation, a reformer, if you like, is simply working to keep that buffer tank between minimum and a maximum pressure range. Okay, so putting this into, if you like, perspective maybe that we can understand, I guess. I think a good comparison to make between, say, the storage of compressed hydrogen and hydrogen generation on demand would be to look at the example of a truck. So this truck here is a North American heavy truck. In the black box here behind the cab itself is a hydrogen fuel cell with 8 large hydrogen storage tanks at 1,000 bar pressure. Now, that hydrogen storage holds about 80 kilograms of hydrogen, and in a heavy duty truck like this, it will give a range of up to about 600 miles. Now, we can also generate that same amount of hydrogen over the same number of hours that it would take a truck to drive that distance with a relatively small hydrogen generator that basically produces around 7 to 10 kilograms of hydrogen per hour. To drive the 600 miles, we only need 1,000 liters of methanol water mix. As it's easy to add additional tanks, or we could be using the existing sort of diesel tanks that would normally be on a truck. But if you wanted to extend that range, it's relatively easy to add another 1,000 liter tank, and you could have basically, twice the range. So I guess when we think about the various factors that are important, to driving anything, whether it's a ship, a car, or a truck that has hydrogen storage on board, is if my alternative is compressed hydrogen on board generation by comparison, generally, if you look at the actual execution of both solutions, doing it using a reformer will end up having a lower capital cost because hydrogen storage is expensive, and also the safety valves and fittings that have to go with that. Second of all, it's a smaller size. Like this photograph here, in this photograph on the right, the green box is basically all the space I would need to be able to do hydrogen production on board. The black box contains my fuel cell and my storage, but if I didn't use compressed vessels, I'd have a much smaller footprint to get that truck traveling the same distance. So about half the space, basically, in terms of footprint. Now, in the States, if I use the example in America here, where there are hydrogen fueling stations and you pay per kilogram for your hydrogen fuel for your truck, if I use methanol to produce the hydrogen, my cost point is going to be around $3.50 to $5 per kilogram of hydrogen produced. If this vehicle is refueled in a hydrogen refueling station, it's more likely going to cost between $10 to $16 a kilogram. Yeah? And mainly that extra cost difference is because the biggest cost of having a hydrogen refueling station is transporting large amounts of hydrogen from where they're produced to the fueling station before it goes into the truck. That's normally the big price of, a factor for hydrogen. Now, and in terms of how this would operate in a truck, regardless of whether it's a stationary or a mobile application, the hydrogen generation system itself has basically three states. So it has what we call on state, where our balance of plant is powered and we are energized and we are waiting for the command from the buffer tank to start producing hydrogen. And we have a operating state where we're actually operating and we're filling the buffer tank itself. And obviously we have an off state where the system is not electrically operated at all. So while the truck is driving and moving along, the time it takes from us to go from, if you like, standby to operational state only takes about a minute. So when we are operating in conjunction with the small onboard battery bank in the truck, this generally can be quite is normally how the system works. It's continually starting, stopping, and its main job is to meet the demand of the internal buffer tank. Now, if we're basically having a load like a truck or a boat or a ship or a shore power type application, normally we would size the fuel cell to meet that particular requirement, and that then would sort of determine the size of the buffer tank that we use, and the whatever sort of batteries or other complementary power would be used would be combined with that. So just, I guess, pulling this into the marine space a little bit closer, this is a barge design from a company we're talking to in Europe at the moment, and this company produces sort of tug barges that are used for applications. And in this case, I think they service the wind farms in the North Sea. So they were looking at not building any more barges using diesel generators anymore. But initially they looked at doing it using 100% batteries, because the job of this vessel is to just go out, turn around and come back. It doesn't stay out of port for long periods of time. Now, when they sat down with some of the battery geniuses, they were told that the cost of putting batteries to provide this power would be in the order of about $3 million in terms of actual cost. But the amount of batteries they would need to operate under the conditions that they had meant would mean that they would have very little, reserve space left to do, carry cargo and stuff like that. So what they looked at doing was reducing the battery bank size, but using compressed hydrogen as the way to range extend those batteries. So in this example here, I mean, the engines on this ship, they are 200 kilowatt, a pair of 200 kilowatt rotating thrusters. The battery bank that they reduced it down to was 2.5 megawatt hours of battery capacity, which weighs about 22 metric tons, or 15% of the vessel's weight. Now, because they're batteries are limited to the amount of times you can charge and discharge them. So if you consider they go out and they come back, that's considered to be one cycle. So those batteries are only good for 5,000 cycles. Um, and to get they had worked out how often they'd be using fuel cell versus how often they'd be using batteries, but they had to design it so that they could get at least 10 years out of the batteries, which is the real challenge if you're limited to 5,000 cycles. So they were going to range extend these batteries using 3 100 kilowatt fuel cells, which would basically sit in this container here. Now, to provide hydrogen for these fuel cells to range extend these batteries, they were looking at 125 kilograms of hydrogen, which basically is a lot of hydrogen vessels in magazines, taking up an awful lot of deck space. The hydrogen storage itself was around 20 tons, nearly the same weight as the batteries. So the solution that we came up with was basically, we said, look, the kilograms of batteries that you need is equivalent to about 8,250 cubic meters. The issue that they had is every time the ship came back to port, a crane would have to lift out each of these magazines of 16 cylinders, drop it to a port, to the side of the port, or to the refueling station, where they'd use even higher pressure vessels to cascade fill these bottles before they could put them back on the ship. Which was, a crane swap every day was not really considered to be very viable. Now, the alternative for this is quite simply our containerized version of our product, rated for 300 kilowatt, and we use the existing fuel tanks that were already there for diesel when they had the original design for diesel generators. So by doing it this way, we could reduce the weight by 50%. We need basically 10 metric tons that would have fitted the requirement for 22 metric tons. The refueling becomes simpler because the same process they use for refueling diesel on vessels that are in the harbor from their bunker on shore can be applied to the methanol. But also the actual per kilogram cost was working out cheaper as well, because where their port was and where hydrogen is produced was like 500-600 miles away. So transporting hydrogen from where it was produced to the bunkering depot in the port itself was much more expensive than just doing it through methanol reforming. So some other examples of these units and what we've done so far. So if you remember our small S series, the one that can support a 10 kilowatt fuel cell. So there are people out there who have fuel cells that are currently running on bottled hydrogen, and they want to look at alternatives. And one good example of this is in the US. So in the US, due to various storms and issues they've had with the grid, there's been a new mandate by this government agency called CPUC. So they have mandated that if you're in telecoms, for example, you must have a backup system that can survive, can keep your service going for 72 hours. So a lot of the BTSs where these fuel cells with hydrogen bottles are actually on rooftops, and simply they're using hydrogen, high pressure hydrogen with fuel cells because they can't put diesel generators on these rooftops. They have issues with noise and vibration and community complaining or whatever. So they used to use 1 or 2 hydrogen vessels, and that would keep the fuel cell going for maybe 4 to 6 hours. But now they have to keep it going for 72 hours. So the reality they were facing was putting as much as 72 cylinders on the top of this roof to do the same job. Now, alternatively, our system, which is in a 2-meter high cabinet, takes up the same footprint as our existing fuel cell, can do the same job with an external IBC plastic tank. So this is another use case example where hydrogen generation through a good carrier fuel like methanol just simply makes more sense than using compressed hydrogen. But again, it's the CPUC are the guys who are enforcing this mandate, which is making this, this situation arise in the first place. Yeah? So taking it a stage further, as I said, we can parallel these small units together. This is a system that I'm on my way to commission in the Philippines at the moment. This is a 20 kilowatt reformer-based fuel cell. It's used to power big BTSs, what they call BTSs that have base station tower sites that have a number of smaller tower sites who are dependent on this tower site actually working. And in the I guess in the telecom sector, it's this sort of power sort of variations made the design and the choice of the fuel cell stack that we used a little bit different to say going for single large stacks itself. So in this case, we have 5 4-kilowatt stacks producing a total of 20 kilowatts. But what we can do is we can cycle these stacks around. So every time it starts, a different stack is the one that starts. And the load in this case can actually vary from 20 kilowatts down to about 2 or 3 kilowatts. So we can turn on one stack and leave the others turned off. It was just the application and the design, having the flexibility to be able to pick different sort of size and technology stacks proved to be quite useful here. So going, say, further up, this is the type of typical design we would use for shore power applications, particularly for the marine industry. This goes into it's quite a specialized 20-foot container. Inside that, we can have effectively a system that can supply 400 kilowatts of energy in a single 20-foot container. So in summary, I guess, what I'm saying here is the, onboard hydrogen generation, any application, whether it's a telecom tower or a marine type application, whether it's on a boat, whether it's shore power or whatever, onboard hydrogen generation where you need it eliminates the need of using high pressure storage. And that, I think, makes a lot of sense for a number of applications. Onboard hydrogen generation, it beats using compressed hydrogen generally on capital cost, on size, physical footprint, on the actual cost of the hydrogen gas produced, and also the range. With the range, I can refill a tank or put a larger volume liquid tank much easier than I can if I have to deal with a high pressure vessel. Yeah? So, for marine applications such as electric generators on ongoing vessels, main sort of power propulsion for inland coastal vessels, power generation for refrigerated containers, or PEM fuel cells, hydrogen fuel cells are really the logical choice to meet these emission standards set by the IMO. Yeah? And that's it, basically. One aspect that I think is quite interesting is the execution of this and the involvement of this is actually quite close to home. Yeah. So there is a very interesting joint venture in play at the moment called E1 Marine. And it's a joint venture between, I guess, 3 highly capable companies, one of which is Ardmore Shipping, a company called Maritime Partners, and Element One. And Element One are the technology company who own the IP of the methanol to hydrogen generation system that RICS produce. Yeah? So I'm a little bit biased here, I guess. Yeah? But this Element One joint venture is focused on driving the reformation of methanol on water to pure hydrogen streams, which can be used to drive fuel cells to produce power for onboard consumption. Yeah? And they see this as a significant step forward in the use of these type of fuels for onboard vessels. And obviously this combination of Ardmore Shipping and Maritime Partners, these guys deeply know and understand the marine environment. So I'm very happy to see JVs like this in place. But what could they focus on? And I think the other thing to bear in mind as well is it's not just about powering ships. It's all about emissions in general. And there is quite a lot of emissions come from other sources other than a vessel itself. So ports themselves can be a significant, a generation of emissions. And there's a recent report produced by a marine port in the States. I think they call themselves Pola, but they identified that something like 1/3 to 1/2 of emissions that actually happen to ocean-going vessels comes from their auxiliary engines, which they need to run while the vessel is docked at port, is berthed at port. And these sort of auxiliary engines, they run everything from electrical power for lighting to water heating to, loading equipment to discharging equipment, stuff like that. And, obviously there is an alternative to this. Like when a vessel comes to port, you could provide shore power. But the reality is the infrastructure and the complexity and the cost of shore-based infrastructure for some of these larger vessels who need megawatts of power can be very prohibitively expensive. And in one sense, yes, you might be able to reduce the emissions at the port by providing grid power to those vessels. But all you're really doing is you're moving emissions further back up the food chain. You're moving the emission issue to the power station level, itself. So in a lot of cases, they don't actually count. So in terms of these vessels themselves, I think there's a good potential of candidates for cold ironing type applications where we don't use the ship's internal engines to provide power. We use either a shore or a barge-based container that the ship can come up to, or we can move to the ship. And I think that's interesting opportunities to look at that space. So when it comes to the sort of these type of requirements for shore power, the power requirements are actually not that excessive. They are relatively doable. And it really depends on the port itself. What is the traffic and what is the frequency of these type of vessels that come to the port, to determine, what type of solution you provide. I guess there's, if you're a ship owner, there's two issues you got to face if you want to make a vessel ready to accept shore power. One is cost, and the second is, I guess, fleet flexibility. So most shipping companies, they don't want to make an investment into an old boat. Yes, they might consider it if it's part of a new fleet or a new boat that they're buying. But these considerations really should be sort of looked at now, rather than later. So this is a concept that we had for a floating barge. Our idea was that, okay, we put the container on a barge and the ships can come up along the barge. And then Dan pointed out that if you put a system on a barge, the barge is technically a boat. So you got more issues to worry about. So this could be on a barge, but it could also be on a pier. If it's in a 20-foot container, it can be moved, or if it's on a trailer, we can move this accordingly. But this would be our sort of immediate proposal for shore-based power, which can be used for some of those smaller ocean-going vessels or barges or tugs or whatever. They can come up alongside, we connect power, and off they go. And the same system can also be used to provide power for reefers, for reefer type applications as well. In the reefer applications, it's quite interesting because the load requirements for reefers, which are basically powering refrigeration units, the power range can be as much as 10 from maybe 2 kilowatt to 10 kilowatt per container, and that can vary as the container is cycling through its chilling process. And I guess one sort of last thing is people are going to ask about safety and stuff like that. So, in terms of safety, there in the implementations of fuel cells that have been done and reports that companies like Sandiga have generated, there seems to be a common sort of theme. Now, obviously, regardless of whatever precautions you take, there's still a chance that injury can occur. But the question for the bean counters here is, how does that injury compare to other types of occupations? So in America, they have this thing called the FAR, the fatal accident rate. So when they assessed, did their assessment in terms of, what the potential, fatality issues were. Yeah. So overall, the conclusion they came to was that in terms of fatalities, the FAR rate, or for overall use of hydrogen itself, is likely to be in the order of only 0.089 fatalities per 1,000 workers, per 1,000 50-year workers, or 100 million worker hours. And that's assuming a worker has 1 or 2 minutes exposure anywhere near these systems, when they're using it, or as part of their work involvement with it. Now, if you compare that data from the other US Bureau of Labor who is doing this, and you look at the statistics of fatal occupational injuries, the risks represented by hydrogen systems are shown to be a similar occupational risk to that of an office worker, and considered to be 10 times less than the occupational risk of some occupations such as truck drivers and machinery workers. So this indicates to me that the risk presented by the hydrogen system to workers certainly is much less than the risk exposure of all transportation and warehouse occupations in general. Now, obviously that covers worker safety. There are other safety factors we have to consider as well, because we're dealing with hydrogen or we're dealing with a liquid fuel. But the issue that generally comes to mind from, high labor type environments is more about the risk to workers than themselves, rather than, the normal sort of safety and stuff that you would implement anyway, because you're dealing with a particular type of product or component. Now, a lot of this study was done again using hydrogen compressed storage solutions. And I would say that even that risk factor would be lower again if you were looking at on-demand hydrogen generation as well. But we would have to see. But anyway, I'm nearly there. Finally, I guess the main takeaway here is onboard hydrogen generation eliminates the need for high pressure on site and reduces issues with refueling. Onboard hydrogen generation beats hydrogen on cost, size, cost of the H2 produced, and range. And I think the really big thing is, for marine in particular, if 1/3 of the hydrogen produced comes from the water I'm sitting in, that's pretty cool. That's pretty cool. Anyway, thank you very much for your time. I hope I didn't overrun my time. I'm quite happy for questions. You can contact me directly. I'd also strongly encourage you to look at Rick's Industries website and also E1 Marine's website too, if you get time. And please feel free to ask any questions you like.
Well, thanks very much, Mark. That was very interesting.
Hope it wasn't too long.
No, you're fine. And I suppose I was only trying to think about it there. How friendly kind of is Ireland to the whole methanol storage, and I suppose in particular our ports? Are they geared up for it?
Well, that's a good question. Is there anybody from the Port of Cork present that would like to stand up and answer that question? Obviously, I believe that Ireland has a big potential to be an early player in this space. I think we have an opportunity to lead by example, and we always do that by putting our best foot forward and providing like a solution that can actually fix multiple problems. So I don't know, because again, I'm not a marine expert, but if there was an opportunity to provide a harbor-based, power system that, an Irish naval vessel could pony up and get shore power from, or, a cargo container can dump some reefers and we can use that. We start small and develop that further. The other thing is, ports have lots of fuel depoting capability. So allocating some of that fuel bunkering space to methanol will encourage other marine companies to come in and to utilize that. Yeah. So I think if Cork happens to be frequented, or Dublin or any of the other ports in Ireland happen to be frequented by particular shipping companies, us and the port should be talking to them. Yeah, for sure. Yeah.
Perfect. I just see there, Jody. Jody has your hand up there. He has a hand up. I think he's a question. If you want to ask there, Jody.
Thank you very much.
Fall asleep, yeah?
Hey, I'm following you, Mark. Mark, what an excellent presentation. Really well done. Fantastic. Really bodes well for the future. For as a green person myself, it really, really bodes well. Are you having any much truck getting it going in Europe, getting it going in Ireland? And the technical questions I want to ask is, number one, the heat generated in the system, how do you get rid of the heat generated? What happens if the system overheats? And what kind of maintenance would be required on board the ship? Is this something you can just put the battery in your car? You can just put it in the back of the ship, whatever it is, and forget about it for a couple of months? Or what's the story involved with that? Thank you.
Okay, so I guess in answer to your first question, there is a ton of activity in Europe at the moment, and this is mainly centered around shipbuilders, and particularly shipbuilders who are building sort of like inner waterway type vessels. We're talking to both the shipbuilders and some of the shall we say engine and turbine companies. Like, I think the thing not to forget here is, like, a lot of ships' engines can run on multiple fuels. So one thought process from some of these ship companies is, I'm going to use methanol as my main fuel in my internal combustion engine. Yeah. And then I'm going to use the same methanol with water that I'm going to take from the ocean. And I'm going to use that when I'm doing maneuvering or I'm at port or whatever. Yeah. So, but there is a lot of interest in that space, but at the moment I see it coming from the shipbuilders themselves and predominantly out of Europe. So obviously, this whole emission, business is good for business, because it's creating this opportunity where these people are coming to us for this. Yeah. In terms of Ireland, it's hard to say, because I guess, my problem is I don't know enough people who, like, the players really, I think, need to be the fleet owners and the port people too. There's got to be something in it for both of them, really. Yeah, they have to work together collectively, and I just can't get around everybody in terms of the Ireland context. In terms of your other question, in terms of heat, we generate heat now. The reformer generates heat, but we recycle that and use it quite extensively ourselves. And our reaction is an endothermic reaction. So it's not likely we're ever going to get heating out of control. Now, on the fuel cell side, when I'm a fuel cell and I'm consuming hydrogen to generate power, I'm also generating heat. So for example, if I have a 100 kilowatt fuel cell, I'm generating 100 kilowatts of heat as well as 100 kilowatts of electrical energy. Now, we can do things with that heat. Ship designers are very good at finding useful ways to use heat for things. So that heat can be utilized. In the smaller type systems, we just, we ignore the heat. But in the larger systems, that heat is a resource that can be utilized. Yeah. I'm just going to show you a quick picture. I don't know if you can see this. I'm probably not meant to show this because this is a project we're working on at the moment, but this is an idea, or this is a design for a ship that's for to go up and down these majorly long waterways in Europe. And the ship can carry either dry stuff, I guess, or containers themselves. Now, if these containers weren't on board, the hatches would be covered in solar panels. This guy wants what he calls a triple hybrid power system, which doesn't actually make sense. But just if you look down here, these are the sources of power. So obviously the main thing is he's using four 400 kilowatt generators that will run on methanol fuel. Yeah? To supplement the generators, he's also using 400 kilowatts of the fuel cell that are going to be sharing the same load bus as 500 kilowatts of batteries. Sorry, 1,000 kilowatts of batteries. So the power system for this boat will be 4 combustion engines running on methanol, 1 fuel cell running on methanol plus water, and these flow batteries, which will be charged by the fuel cell. And he'll have a small bit of power generated when his hatches are closed from solar PV. So this is the type of stuff that we're getting dragged into now. So presumably, while this boat is out in the ocean away from ports, they'll run on the methanol engines, combustion engines. But when it gets close to the port, or they want to do any maneuvering of their bow thrusters and stuff like that, they'll use the fuel cell / batteries to do that. But this is what I see as being quite typical now. Yeah.
Yeah, look, that's fascinating stuff. I don't know, has anyone any other questions, guys? I'm just cognizant of the time that Mark is in Indonesia, and it's, I think, about nearly 2 a.m. his time there, so he should be in bed.
Right, I got Indonesian wine. I'm okay. Yeah.
Just one more, Dan, about the maintenance. What kind of maintenance involved?
Oh yeah. Okay. Sorry. Yeah. So in terms of maintenance, there is actually quite a small amount of maintenance to be done. Like the reformer itself, there's only 2 sort of components that are mechanical. There's a fan that blows air in, and there's a fuel filter. Now, generally, the fuel filter would be replaced every maybe 5,000 hours or something like that. The fuel filters, we'd have a pneumatic sensor on them, so if we detect that the methanol is getting clogged up or something, the issue with fuel contamination, an alarm is raised anyway. So the reformers really very little maintenance. They're designed to run for about 15,000 hours. Now, on the fuel cell side itself, again, there's no moving parts. There's only air filter to worry about. Fuel cell will last 10,000 hours as well before we do some part replacement. But there's no like oil change, oil filter, levels or anything like that to be considered at all.
So that's great. Listen, I suppose we'll just finish up. Maybe if Liam Doyle there, our chairman, would like to maybe say a few words just to finish the meeting.
Hello, Mark. On behalf of the Cork branch of the IMRS, I'd like to thank you for a very enjoyable presentation. And a lot of information was displayed, and thank you very, very much. I'd also like to thank Dan for organising the talk tonight, and hopefully we'll go from strength to strength. We had a good crowd. Well, we had a reasonable crowd tonight, and I'm glad that everybody joined. And I'd like to thank everybody that came on tonight. Thank you.
No problem. You're all welcome. Yeah. So Dan will have a copy of this recording and also the PowerPoint, but Dan also has a number of those reports that are referenced in the PowerPoint as well. Yeah. So if you're interested in reading about some of where this information comes from, the reports are a good source. Yeah.
Oh, thank you.
That's great. So listen, it's up to me. We'll just finish up the meeting, and I just say thanks very much, and thank you, Mark, for tonight's presentation, and good evening to everyone.
Yeah.